So, hi guys, welcome to my YouTube channel. Today we will be looking at a mathematical proof towards the centripetal force formula for circular motion. And so we all know, this will use calculus, some basic calculus. We all know that the standard force, centripetal force formula is this. Wait, I'm actually going to. Okay, so pick a nice color to write it. We know this is the formula. Fc, and it's a vector, although I'm only looking at the magnitude now, is mv squared over r. And that's what we're trying to prove. So, trying to prove this mathematically, we can start with the idea of circular motion as it is, a circle. So, if we draw a circle here, we're just doing black. I will just make it a bit bigger so that we can view this neatly, because the circle is very important. So we can increase the size of it. So we have our radius. Let's do that in green. And we have our instantaneous velocity here, which is a vector. And of course, this radius will be on our x and y axes. So if I just draw in our x and y axes here, let's imagine this circle's center is 0. So if I drop in 0 here, and we have our x and y axis. So mathematically, we have this relationship that for a circle, the equation of a circle is given by x squared plus y squared is equal to r squared. And we know this. Now this is how we describe a circle on the two-dimensional coordinate plane axis. So if we now try to think about this, the velocity will be the change in displacement over change in time. And so it's a vector that tells you how x and y are changing. So if we think about this, that we can differentiate this right now. So we can go back to black. And if we take the derivative of both sides with respect to t, dy squared over dt is equal to dr squared over dt. I'm actually make this a bit smaller so that we can some nice space later on. So this is what we're looking at. So when we differentiate this, this is what we get. So let's differentiate. It's x is a function of time, of course. So we have, by the chain rule, we have this 2x power rule, and then we have the chain derivative, which is dx over dt, plus 2y times dy over dt. X and y are both functions of time, we're assuming. This is our x displacement and our y displacement. And r is, of course, a constant, so we let that be 0. Now we get x dx over dt plus y dy over dt is equal to 0. So we have just got a relationship for x, y, the change in x and change in y. So how this I'm just going to reduce the size here because so we have a relationship here. And of course now we can see that an important idea is that as we know, velocity is changing displacement over time. The velocity is a vector. So we can have Vx, which is equal to dx over dt, and we have our Vy, which is equal to dy over dt. Okay, yeah. So I will just for notation purposes, I will let this be Vx with Vy. So now we get the equation Vx plus y vy equal to 0. Now let's differentiate this again. So if we move down a bit, now if we differentiate again with respect to t, and we'll get into the logic behind why we're doing this right now. And the main idea is that force, as we know by Newton's second law, is related to acceleration, and we want to obtain some kind of expression for the acceleration, centripetal acceleration, as we know. And if we do this now, we just have a little product rule where we have x dvx over dt plus vx, this is basic differentiation, x over dt plus y dvy over dt, running out of space here, plus vy dy over dt, and of course the derivative of 0 is just 0. So we have come to this. Oh, sorry, 1 second. Let me just know what we have here. So we have a 0 here, of course. I can now change this to get a bit more space because the main idea is going to come now. And this is the interesting part. So we can just, till now we haven't really thought of it as vectors. Now as we know, just like we looked at velocity, acceleration too is a vector, and we know it is such that we have ax, which is equal to dvx over dt, which is the second derivative of displacement with respect to time, and we have ay to dvy over dt. So if we go back to where we were, this is where we are, we can now replace this to say x times ax plus, we know this is dy over dx over dt is equal to bx, so it's just bx squared, plus y times ay plus vy squared. As we know, dy over dt is equal to dy. And now here's the trick. This is what we have to understand from a mathematical perspective, that x and y are the vector components of displacement. Oh, sorry, 1 second, let me just put this in. Oh, it's tricky. Okay. So x and y are the components of displacement. So if we put this here, let's write this here. I'm going to actually make this smaller too, so that we have enough space to write this, because this is important. X and y are the, as I said, the vector of displacement. And we know, so I'm writing here. Excuse me. Okay. So we know our vector displacement is such that we have xi plus yj. And we know our acceleration vector is ax I plus y a plus like ay. Now here's the trick. If we look at our expression here, we can see something. Let's start with this. Our velocity is a vector too, as we discussed, and that's why we need to know a bit about vectors here. When we have a velocity vector equal to vx I plus vyj, therefore the modulus, the magnitude of this, will be the root of vx squared plus vy squared. We know this. And now what all we need to know, now we get, is the magnitude square of the velocity. Instantaneous velocity would of course be the square, the sum of the squares of each component. And this is important, because now we can express our expression here as x times ax plus y times ay plus the magnitude of velocity squared equal to 0. We're almost there. So now here's one more trick. Let's just move this to the other side to keep it simple. X ax plus y ay is equal to minus square. Yeah. So now here's another idea we need to look at. As we've seen this, we have this expression, but we know x, y, which are the components of the displacement, and ax, ay are also the components of the acceleration, as we saw here. So if we take a vector dot product, that's what we need to do. So I'm going to do that in green. This is also an important idea. Just to keep the colors a bit the same. So we get s dot a. What do we get? Well, we have xi plus yj. This seems very trivial, but it's important to understand that this is really the crux behind this this idea. So we have ax, ay, j. And of course, as we compute the dot product, we get ax plus y, ay. And that's exactly what we have here. So we can easily spot from this that this is the dot product between the two vectors, and the dot product, of course, gives us a scalar. It makes sense, why? Because on the other side we also have a scalar, which is a magnitude. So I'm going to write this in red now here. No, I'll write it in black. Here, almost done. So we have the displacement dot the acceleration gives us minus v mod square. Okay. So our acceleration vector will be equal to minus velocity over the displacement vector, which may not really make sense, but we're going to take this from a mathematical perspective. Can't really divide. Dividing a vector seems a bit the idea seems a bit difficult, but if we think about this, the dot product itself gives us a scalar value. So if we're just thinking that if I'm going to take the magnitude now of this vector, so if I get this, so if I take the magnitude, what do I get? When I take the magnitude, of course, this becomes a positive, and this already is a magnitude, but we get the magnitude of s. And here's an important idea. We'll go back to Pythagoras. Simple Pythagoras here. The r is constant, the radius. And if we think about it here, for the displacement, any displacement, it's just r square is equal to x squared. Sorry. Sorry. So let me just get the rubber here. So we know that r is constant. R is constant. Therefore, the mod of displacement is constant, as implies. So we know what is, because displacement, the mod of displacement is equal to the root of, as we saw, r mod of r is equal to the root of x squared plus y squared. Therefore, by simple Pythagoras, we can actually illustrate this here quickly. We have our r on the circle. We have our, here's our x, y, x, and this is our r. R squared is equal to y squared plus r squared, x squared. And therefore r would always be the, and we know the magnitude of the displacement vector is of course root of both components squared. So all we have to do here, we come in and we just get this. The magnitude of acceleration is equal to magnitude of velocity squared over r. And this is the centripetal acceleration actually, because if I'm going to just write it now in our format where we know AC is equal to V squared over R, where V squared we're just considering V to be the magnitude. And now, of course, via Newton's second law, I can go here, I go to blue, green, as our sum of force mass times acceleration. And the net force is, of course, the centripetal force here, implies in red, Fc is equal to mass times AC. Fc is equal to mv squared over r. And that is a mathematical proof to the centripetal force formula. So I hope you enjoyed. Please, if you like the video, don't forget to like, share, and subscribe. And thank you for watching. I hope to see you next time.